In this video, I'm going to talk about Faraday's law. Consider a metallic loop. There's a magnet here with north pole on this side, south pole here. The direction of magnetic field is from north to south. But at this point, this is the direction of magnetic field, B. I'm going to move the magnet into the coil. That would induce a voltage in this coil. If you move the magnet away from the coil, again, there is an induced EMF or induced voltage produced in the coil. The reason for this is when you move the magnet into the coil, you are changing the number of field lines passing through the coil, or you are changing the magnetic flux. Phi B is the magnetic flux. Phi B is the magnetic flux. The equation for phi B is BA cosine theta. When you move the magnet into the coil, you are changing the magnetic field inside the coil, and thereby changing the magnetic flux. So Faraday's law states that if you change the magnetic flux, change is d by dt, rate of change is d by dt. If you change the magnetic flux, d phi b by dt, you'll produce an induced voltage. There is a negative sign as well. This is for a single loop. If you have multiple loops, multiply with the total number of loops. That will give you the total induced voltage, minus n d phi b over dt. This is called Faraday's law. Phi b is BA cos theta. So I'm going to replace phi b. V induced is equal to, let's say n is equal to 1. The equation will be minus d phi b over dt. So V induced is equal to minus d by dt of phi is the magnetic flux, that is BA cos theta. Alright, so there are three ways you can change the flux. You can change B or A or even theta. Case number 1, we are changing magnetic field. A and theta are constants. I'm going to modify this equation. V induced is equal to negative sign here, minus A is a constant, take it outside. Theta is a constant, so cos theta is another constant, take it outside. Then we have B here, so dB over dt. So this is the equation for induced voltage if you're changing magnetic field. Case number 2, I'm going to keep magnetic field and angle as constants, and I'm going to change the area. Okay. So changing area A. So B and theta are constants. The equation will be, so this is our main equation. I'm changing only area, so B and theta are constants. I'm going to take them outside. V induced is equal to minus B is a constant, theta is a constant, so cos theta is a constant. Then we have dA over dt. Case number 3, I'm changing the angle, theta. Theta is the angle between magnetic field vector and area vector. These are constants. V induced is equal to minus B is a constant, A is a constant, d by dt of cos theta. So V induced is equal to minus BA. D by dt of cos theta is minus sine theta times, we have theta here, but we are differentiating with respect to t, so we should multiply d theta over dt. D theta over dt is the angular frequency omega. So I'm going to replace d theta by dt with omega. V induced is equal to minus BA times minus sine theta times omega. Minus into minus is plus, so V induced is equal to omega BA sine theta. Example 9.1, potential difference induced by a changing magnetic field. A current of 600 milliamps is flowing in an ideal solenoid, resulting in a magnetic field of 0.025 Tesla inside the solenoid. Then the current increases with time t according to I of t equals I0 times 1 plus 2.4 t square. If a circular coil of radius 3.4 centimeter with n equals 200 windings is located inside the solenoid with its normal vector parallel to the magnetic field, what is the induced potential difference in the coil at t equals 2 seconds? So we have a solenoid. Current is flowing through the solenoid. Current is given as a function of time. If you put different values for time, you'll get different values for current. So current is changing. There are 200 windings. N is equal to 200. The radius of the coil is R is equal to 3.4 centimeter. When current flows through a solenoid, it creates a magnetic field. But this current is changing, so that creates a changing magnetic field. The relation connecting magnetic field and current of a solenoid is B equals mu 0 Ni. Mu 0 is the permeability of free space. N is number of turns per unit length. We can find the equation for current from here. I equals B divided by mu 0 N. Okay, we're going to call this equation number 1. We have the equation for current. Current as a function of time. I of t is equal to I0 times 1 plus 2.4 t squared. So using this equation, I can write I of t equals B of t over mu 0 n, and I0 is equal to B0 over mu 0 n. Substituting these two equations, 1a and 1b, in this equation 2, substituting equation number 1a and 1b in equation number 2. I'm replacing I of t with B of t over mu 0 n, replacing I0 with B0 over mu 0 n, 1 plus 2.4 t square. Cancel out mu 0 n and mu 0 n. That's the equation for magnetic field as a function of time. B of t equals B0, 1 plus 2.4 t square. Or you can simply replace I with B. You'll get the equation for magnetic field as a function of time. Now let's use Faraday's law. Let's call this equation number 3. Using Faraday's law, we need to find the potential difference induced in this solenoid. In this question, magnetic field is changing, so I'm choosing the first equation, which is V induced is equal to minus A is a constant, theta is a constant, so cos theta, dB over dt. But we have multiple windings, so I'm multiplying this equation with n. Minus Na cos theta dB by dt. N is 200. Area is pi r square. R is 3.4 centimeter. So pi times 3.4. We need to convert centimeter to meter. So multiply with 10 to the power minus 2, the whole square. 3.63 times 10 to the power minus 3 meter square. Theta equals 0. So cos 0 is 1. Cos theta is equal to cos 0, which is equal to 1. dB by dt. Okay, so dB by dt, b of t is b0 times 1 plus 2.4 t square. I'm substituting here. So d by dt of b0 times 1 plus 2.4 t square. dB by dt is equal to multiplying b0 into the bracket. So d by dt of b0 into 1 is b0 plus b0 into 2.4 t square is b0 times 2.4 t square. b0 is a constant. So dB by dt is equal to, separating the terms, d by dt of b0, d by dt of b0 plus d by dt of b0 times 2.4 t square. The first time we have only b0 and we are finding, we are differentiating b0, so that's 0. D by dt of a constant is equal to 0. So dB by dt is equal to 0 plus, here we have b0 2.4, b0 times 2.4 t square. So take the constants outside, b0 and 2.4 times d by dt of t square is 2t. So dB by dt is equal to 2.4 times 2 is 4.8 b0 times t. T is 2 seconds. It's given in the question. We need to find the potential difference when time t equals 2 seconds. I'm replacing t with 2. 4.8 b0 times 2 is 9.6 b0. dB by dt is 9.6 b0. So I'm going to replace dB by dt with 9.6 b0. So V induced is equal to minus n is 200. There are 200 windings. Area is 3.63 times 10 to the power minus 3. Cos 0 is 1. dB by dt is 9.6 b0. b0 is given 0.25 Tesla, 0.025 Tesla, b0 is 0.025 Tesla. So replace b0 with 0.025 minus 200 times 3.63 times 10 to the power minus 3 times 9.6 times 0.025 minus 0.174 volt.